All right, then. So we're back, and we're not quite done with chapter 11, and which we'll finish today. And then we'll start 12. In the meantime, I hope you're working on your midterms. Remember, they should be ready by Monday at midnight. So you've got plenty of time. And I'm sure you've already noticed that it's not as long as the first midterm. And so, just take your time and get it done properly. It's exactly what we've been doing. The challenge, as always, is to make sure you understand what each problem is all about, and then using the formulas that we used in the slides. And so then now at the end of the course, which is rapidly approaching, chapter 11 and 12 will constitute the final exam. It will not be comprehensive, which I'm sure will make you happy to hear that. So what we still have to do is finish 11 and 12, and then we'll do all the corresponding problem sets and the sample final, and then we'll be done. It's hard to imagine that we are within striking distance of the end of the semester. It's been a long one, hasn't it? Oh, yes, it has. All right. So anyway, let's get back to 11. So we studied several different kinds of new probabilities, and we analyzed them all with these charts based on the student body at this business school. And so we were able to determine how to calculate joint probabilities, which are the probability of two events both being true at the same time. For example, the probability that a person in the school is getting a bachelor's degree in finance, we saw that equals 130 out of 500, or 26%. And we discovered that by simply looking at the row and column where we find the bachelor's degree students and the finance majors, and we can see where they overlap. There are 130 students in this category out of 500 total. So it's a very simple process. Now, we also saw what are called marginal or unconditional probabilities. Oh, here we go. Here are the calculations for bachelor's degree in finance. So 130 is the number we're looking for, divided by the grand total is 26%. And this is referred to as a joint probability because, like I said, two different things are true at the same time. All right, so we did all of those. And then we were introduced to marginal or unconditional probabilities, where what we're essentially looking for here are row or column totals divided by the overall total. So, for example, if in this case, I just want to know the probability that a student is majoring or getting their bachelor's degree regardless of their major. So we're adding them all up to come up with 400 out of a total of 500, and we get a probability then of 0.8. All right, and so we can do the same thing with the rows and the columns. For example, we also went ahead and looked at the probability that a student is majoring in accounting, regardless of whether they are bachelor students or master students. And so we ended up with 215 over 500. All right, so we still have one more type of probability to define before we can introduce our multiplication rule. Now, one more step here. We also saw that this table can be arranged slightly differently by simply dividing all the totals in here by the grand total of 500. And so by doing that, all of these numbers are now probabilities instead of raw totals. And sometimes it makes things a little bit simpler. But the only thing is we lose the information about how many people are in each category. So if we need that information, this is not the right way to go. But if we're only interested in probabilities, this is a good idea because that makes things a little bit simpler. All right, now here we go. Conditional probabilities. We saved the biggest one for last. This is a case where a probability of an event depends on whether or not another event is true or false. Okay, in other words, the word conditional means it depends on another event. So this is the ratio, as it turns out, of a joint probability to a marginal probability. So let's see how this works. Now, the wording of this is very important. The probability that a randomly chosen student is majoring in marketing, which we've already done, but all of a sudden there's this new piece of information. Given that he or she is pursuing a bachelor's degree. So what this means is that we know that the student is getting a bachelor's degree. That's already been established. Okay, so we know that the student is getting the bachelor's degree. So what that means then is that we can essentially ignore all the MBA students when we calculate this probability. We're going to take a slightly different approach. So what we're going to do then, first, we're going to introduce some new notation. We're going to write this question in the following way. Remember, by the way, don't forget T represents marketing. So I'll put a T here and then this big slash. And this slash can be expressed as given that. So this is the first time we've seen this. Now B, of course, means that the student is getting a bachelor's degree in business administration. And so T, of course, means majoring in marketing. So you can see this is very different than just asking the probability of T. This is different because now we know that the student is not getting an MBA, they're getting a bachelor's degree. And that will affect the probability because the proportion of students who are majoring in marketing is different among the MBA students as the bachelor students. And this type of probability is known as a conditional probability. And you can see why it's different, again, because of this extra piece of information that we know for a fact that the student is getting their bachelor's degree. Now, we need two pieces of information to solve for this. All right, formally, a conditional probability like this is written as we're going to have a ratio of the joint probability of both of these events being true. And then we're going to divide by the probability of B. Okay, so in other words, in the numerator, we will always have the probability that both of these events are true. And in the denominator, we always have the probability of this second event. And so this is sometimes called the conditioning event. You don't have to remember that, but that's what goes in the denominator here. All right, so now it's easy to remember this because this does kind of look like a division sign over here, but it's not. T given B, this is pronounced the probability of T given B, which is just shorthand for saying given that B is true, is this formula. So now what we need to do is go back to our chart and look up both of these probabilities and fill them into this formula. Okay, so we can do that right directly from the chart. I'll just give you a minute to catch up. All right, so how would we do this? So the probability of T and B is right here. And the probability of B is right here. So that implies that the probability of B, T given B is the ratio of these two numbers. Which is 0.18 over 0.80, which is approximately equal to 0.225. Okay, I'm running out of space here. I'll put it right here. Okay, so in other words, so once we know that this is definitely a bachelor's degree student, the probability that he or she is majoring in marketing is 22.5%. If we just asked about marketing in total, I'll put a note down here. The probability that we're majoring in marketing is 0.22. So they're close to each other, but they're not the same. So the reason for this is because the proportion of MBA students majoring in marketing is different than the proportion of bachelor's degree students who are majoring in marketing. And that's why once we know that this person is studying or getting their bachelor's degree, that changes the likelihood that they're majoring in marketing. So in most cases, these two will be different from each other. All right, so why don't we try another one just to get some more practice with this. So I hope you get the idea. So each time the setup will be exactly the same. So for example here, what if I ask the following question? I want to know that a randomly chosen student is getting an MBA given that he or she is majoring in accounting. Okay, so let's see if that works. All right, so the probability that a randomly chosen student is pursuing an MBA given that he or she is majoring in accounting. So let's write out this with the symbols M and A. Well, actually first, let's write it out like this. It's M because we want to know the probability that they're pursuing an MBA. This is the part that we know, the A part. We know that this person is majoring in accounting. With that information in hand, we want to know the probability that they're getting their MBA. Okay, so this is given that. Now the formula would then be this ratio. And again, in the numerator, you have the probability of both events. I'll note that right here. Over the probability of the given event. Let's call it the given event. And always it works out the same way. So now what we have to do is go back to our table and find these two probabilities. And then we can plug them in and we'll have our answer. All right. So once you've done a few of these, you'll realize they're really not that complicated, but you can see how this is not something you dive right into. It's a good thing we built up to this by introducing joint probabilities and unconditional probabilities. All right, so going back to the table, remember we're looking for the probability of M given A. M and A is here because that's MBA and accounting. And just plain old A is 0.43. All right. That's approximately equal to 0.16, let's say 3 or 1.28. That's fine. Okay. So again, I would remind you, and then again, let's just note that the probability of M by itself is 0.20. So they're not exactly the same, are they? No. And it's again because the proportion of MBA students who study marketing, accounting rather, is different than the proportion who study or are getting their bachelor's degree. All right, so in other words, 7 out of 20 down here are getting their accounting degree. Up here in this group, it's 36 out of 80. Those are two different ratios. So all of the conditional probabilities are exactly the same. So the only thing that changes is what is the event that you actually know. All right, I'll tell you what, let's make up a new one. One more just to get some practice. Let's say, I think I can fit this all in one slide. What is the probability that a student is majoring? Let's see if we can do something different. Given that he or she is an MBA student. All right, so let's see if I can squeeze this table in here. It's always nice when it all fits into one place. Oh, I don't think that fits. Hold on. Let's see what I can do. There we go. It fits. Woohoo. Okay. Oh, you know what? Well, all right. Ignore those. I wanted one that doesn't have boldface. Let's get rid of this one. Oh, here we go. Let's steal this one. All right. So oh, good. So there's plenty of room. So just keep in mind that this represents the probability of F given M. Because we know that this person isn't, we know that they're getting their MPA. We want to know the probability that they're studying finance. So formally, that's going to be this ratio. And so F and M is just right here. And the MBA students are here. Okay, so that's 45%. And then you're done, and that's it. So they're all exactly the same. Now, we finally are ready to introduce the multiplication rule. And you'll see why all this buildup was necessary, because the multiplication rule is defined in terms of conditional probabilities. Now, it turns out there's actually two equivalent ways of expressing this rule. So we'll look at them both. So here's the first way. And you can see, look at that. We need a conditional probability to do this. So first, note that this is the probability of an intersection, which means A and B, or B and A are both true. And it's written in terms of conditional probabilities, or at least one conditional probability and one unconditional probability. So this is the probability that, sorry, both B and A are true. Okay, and remember, this is the symbol for intersection, which is also in terms of English the same thing as and. What's the probability of B and A? Both of them. And if you notice, this is a joint probability. Now, before we were doing these with a table, but we don't always have access to a table. Every situation is different. So for some cases, without having a table like that, this is what we have to do instead. we use this rule if we don't have enough information to simply look it up in a table. So it's an important rule. Now, let me show you the other equivalent version of it. Remember, there's always two ways of doing this. You'll see that they're very similar to each other. Okay, but they're not the same, are they? In fact, I'll tell you what, why don't we copy this one onto the second slide so you can see side by side how they're different. Okay, so they are different. It's a very subtle difference, but it's an important difference. All right, so now in some circumstances, the first formula works the best. And in some cases, it's the second one. Sometimes we may not have the right information to do one or the other. So it's good that we have both of them available to us. So you'll always want to use the one that makes the most sense, of course. All right, so let's look at a quick and simple example. We'll go back to our favorite examples, decks of cards. So first we'll start by assuming that a card is chosen from a deck. And this time we want to know, well, first A is the event that the card is an ace, and second, B is the event that the card is black. Okay, well, we know a couple of things here. First, before we go any further, let's just note that the probability of A is 4 out of 52. And the probability of B is 26 out of 52, which is 1/2. All right, now, what question are we being asked, though? What's the probability that the card is black and is an ace? So that's the probability of B and A. All right, well, let's try this with the multiplication rule. And of course, there's two ways of doing this, as we've seen. So let's start with the first approach. So that means we need to know the probability of B given A and the probability of A. Well, A is easy. We've just seen that it's 4 out of 52 or 1/13. Actually, I might as well put that in here as well. Okay, so that's easy. The trickier part is B given A. So here's how we have to think about it. B given A. Now, what this means is that the card we chose is known to be an ace. Now, if obviously I'm assuming everyone's familiar with the deck of cards, of the 4 aces, 2 are black and 2 are red. There are 2 red aces, 2 black aces. So therefore, if I see that I have 4 aces in front of me, I know that 2 of the 4 are black. And therefore, the probability is 2/4 or 1/2. So now I can combine these to come up with the answer that we need. So remember, we just got through proving that the probability of B given A is 1/2, and that A is 1/13. If you multiply those out, you get 126, which is approximately equal to 0.0385. All right, now, what about the other approach? Suppose now the second approach would be this one. So this time we need the probability of A given B and B. Now B, as we've already seen, is 1/2 or 26 out of 52 because there's 26 black cards in a 52 card deck. A given B is the tricky one because what's happening here is that you see that you have one of 26, you've got 26 black cards. Two are aces. In other words, of all the 26 black cards, we have 2 aces, we have 2 twos, 2 threes, 2 fours, all the way up to 2 jacks, queens, and kings. So 2 out of 26 cards qualify. 2 of the 26 black cards are aces, so therefore this probability is 1 out of 13. And so when we substitute these into the formula, well, it looks pretty similar, doesn't it? It's 1/13 times 1/2, 126, and once again, that's 0.0385. Now, I do want to point out here, though, that in this case, at least, using the rule wasn't absolutely necessary. It was just one option that we had available to us because we know how the deck works. Okay, so in this example, using the multiplication rule was not absolutely necessary. We know that there are 2 black aces in a deck of 52 cards. Therefore, the probability of choosing a black ace is 2 out of 52 or 1 out of 26, which again is approximately equal to 0.0385. So in a case like this, at least we know how to confirm that we did it correctly. We didn't absolutely have to go through all that trouble. But there are other cases where we would have had to do this because we didn't know what the sample space looked like. So yeah, there's usually multiple ways of approaching these probabilities, and this is one of those many cases. So we can use the multiplication rule for any case where we're looking for the probability of or a joint event, but sometimes there are other things we could do as well. Okay. So just be aware that in a situation where you're asked to calculate a probability, you can feel free to use whatever event or whatever technique makes the most sense. It probably won't say in a problem, you must use the multiplication rule, although I guess it's possible. But usually you've got multiple options with calculating probabilities. All right, now you might remember that when we were dealing with the addition rule, we had a special case. We created a simplified addition rule. Let's go back and review that. The simplified addition rule, let's go back and refresh our memories. There we go. The full addition rule was this. And then we discovered that under certain conditions, we can use the simpler version right here. And that could only occur when we had what we call mutually exclusive events, which means that they can't both be true at the same time. A similar situation arises with the multiplication rule. In other words, under certain conditions, we can use a simpler version of the multiplication rule, which I'm about to show you. But before we do that, I have to explain under what conditions we can do this. So we're going to introduce the concept of independent events. Now, do not confuse this with mutually exclusive events. Mutually exclusive means 2 events can't both be true at the same time. Independent events are events that do not affect each other. All right, and we're going to formally define that in a minute. But first, let me show you an example of what or some simple examples of events that are independent of each other. All right, so just remember, these are two events where they do not influence each other, which simply means that if we know that one is true, it doesn't affect the probability of the other one. All right, so for example, suppose that A is the event that, let's say John gets an A in Math 1060, and B is the event that the weather is unusually cold. Well, is there any reason to think that those two are related to each other? Absolutely not. So therefore, John's grade, since John's grade does not depend on the weather, and the weather certainly does not depend on John's grade, we can say that these events are independent of each other. Okay, now there's a much more formal way of explaining this, but I want you to get the intuitive feel for what exactly does it mean for two events to be independent. It basically means they're unrelated to each other. And so the probability of one is not influenced by the probability of the other one. Okay, so now that you know that, now let's see what the formal definition is. Oh, here's one. Here's another case where the events are independent. A card is chosen from a deck. A second card is chosen after replacing the first card. So what that means is that when we take the second card, the entire deck is still intact. So the events that we are defining are the first card is red and the second card is red. Now, by the way, I just want to go through a little detour here. What we just did here with this case is we took the deck, we picked our card, and we observed the card, and then we put it back and took another one. I hope this little diagram makes sense to you. This is referred to, and you don't have to memorize this, but sampling with replacement. Now, because the entire deck remains when we pick the second card, the outcome of the first card will not influence the second card. And that's what we would expect to see with sampling with replacement. The outcome of the second draw does not depend on the first draw. Now, I want to show you a different scenario that could potentially happen as well. What if we did this instead? Here's our deck. We pick a card, and then we pick a second card. We did not put the first one back. This is called, as you can probably guess, sampling without replacement. And therefore, the outcome of the second card draw, I should say, does depend on the first draw. And you can see why, because let's say the second card is red. The probability of choosing a red on the second card depends on whether or not the first card was red, because if it was, there are fewer red cards in the deck compared to if it was black. Plus, there's a card missing too. So without replacement, the outcome of the second draw does depend on the first one. So they're two very different scenarios. All right, so I just wanted to mention those as we go along because we'll use these examples again in the future. But here we're using the first case, sampling with replacement. So what that means then is that the probability that both cards are red, well, remember each card, or every time you draw a card from the original deck, there's 26 reds out of 52. That means there's a 1/2, well, the probability is 1/2 that the card you pick is red. Once you put the card back, the probability that the second card is red is also 1/2, or 26 out of 52. So what you can claim then is that the probability of A is 1/2, the probability of B is 1/2, but furthermore, the probability of B given A is also 1/2 because the fact that the first card was put back means that whether A is red or not, the probability of B, the second card being red, is still 1/2. So the fact that we drew or did not draw a red card in the first draw, does not influence the second one. So therefore, to calculate the probability that they're both red, by applying the multiplication rule, we're going to do it like this. When we plug these numbers into the multiplication rule, you'll see that we simply end up multiplying 1/2 times 1/2, which is 0.25. Because remember, this is the same as B. The fact is that the A does not influence B. So therefore, these actually mean the same thing. And you can think of this as P, probability B times probability of A. Now that should give you a hint. But so what I'm going to do now is show you the full formal definition of what it means to be independent. Okay, now we know the example John and the weather is fine, but we need something a little bit more rigorous than that. So if A and B are independent, as they are with the drawing with replacement, then the following two things must be true. Both of these must be true. Okay, so as we've just seen, the probability of B given A is equal to the probability of B, and furthermore, the probability of A given B equals the probability of A. And so the way to think about it is that this information does not influence our probability. It's irrelevant. It doesn't matter. So therefore, these are equal to each other. Now, if this is true, then our multiplication rule becomes really, really simple. And I mean really simple. Why do I say that? Okay, because I'm going to show it to you now. The two equivalent versions of the multiplication rule can be expressed in the following way: when the events are independent. Here we go. Now watch how easy this is. Oh, now that's a lot simpler. Look how easy that is. All right, wow, that looks pretty straightforward, doesn't it? It's nowhere near as complicated as the full multiplication rule, but remember, we can only use this when the events are independent. All right, so you know what I'm going to do? I'm going to make up a new example here. We could always use more examples. All right, how about this case? Suppose a coin is flipped twice. The following events are defined. A equals first flip is a head. B is the event. The second flip is a head. Okay, now you can see where this is going. The way a coin works is that once I flip the coin, the chances of getting a second head, let's say the first flip is a head, does that influence the probability of getting a head on the second flip? And the answer is no. Why would it? The coin doesn't remember what it flips it has already had. So each flip is completely independent of the other flips. So therefore, the flips are independent of each other. Further, PA equals a half, and PB also equals a half. Therefore, using the simplified multiplication rule, we can say that we can use, let's say, B and A. Let's see. Yeah, I run into this problem sometimes. Finding this, there's certain symbols that are a real pain to find. I'm going to have to look this up for a second. Oh, no, I have a better idea. I'll just use the equation editor. It'll be so much quicker. Oh, you know what I forgot to do? I forgot to define the probability that we need. What is the probability that both are heads? Okay, that's really the point of all this. What's the probability that they're both heads? Okay, so we'll use the simplified multiplication rule. And what is that going to give me? Okay, now see how easy that is. It's just the probability of the two individual events, 1/2 times 1/2, which is 1/4. All right, there we are. And that's how it works. But remember, keep in mind that this is only possible because of the fact that A and B are clearly independent of each other. Otherwise, we would have had to use the full-blown multiplication rule. All right, well, I think we're done here with this. So let's do this. Now, the next chapter, and by the way, the final chapter, is chapter 12. Now, I did say earlier on that 11 and 12 go together because 11 is probability theory and 12 is statistics. The two of them belong together because one is derived from the other. And statistics is more, unlike probability theory, which is fairly conceptual. With statistics, we're going to spend a lot of time churning out results. So in other words, it's more calculator intensive than 11. 11, the actual calculations are not hard. The hard part is figuring out what to do with the numbers that we have. In chapter 12, pretty much we just have a bunch of formulas that we use, but the formulas themselves are a little bit more complicated. Not a whole lot, enough though, that we have to be very careful with them. So I do have some interesting videos here to introduce us to the topic. Now, one of them, believe it or not, is a comedian who makes his living making jokes about relatively serious topics. This is a very short clip of his act where he talks about statistics. So we'll start with that, and then we'll look at a more serious video, which is more of a broad overview of the field of statistics before we start diving into the chapter. Okay, so let's get this one out. Very hard to find comedy in statistics, but this guy manages to do it. So let me send that off to you. And let's do this. I realized this. And they choked when it's done. Not done, just all right. How was that? No, don't look at bears. Yeah. Now this guy, this is where I mean, this is what he specializes in. Now, there's one more here that well, you know what? We've got a little extra time here. This has nothing to do with math. It's the same comedian, but he's talking about how people misuse PowerPoint. So I thought maybe just because we have a little extra time here, we could check it out because it is funny. Even if you've never done a PowerPoint presentation in your life, you see them all the time in this class. So I thought you'd like this one. And then when that's done, we can take a look at our actual statistics, our next serious statistics video. Okay. So let's check this one out first, just because I think you'll like it. That's the only reason. Um, even like I said, even if you never ever do a PowerPoint in your life, you'll like this video because you probably have actually been in classes where there were bad PowerPoints being used. So, all right, let's check this out. All right. Have you ever been in a class where they committed any of those mistakes? I hope not. He's good. Um, oh, that's right. I don't care about the microphone as long as the picture's not on because oh, but that does that cause problems with the sound?
It was just at the beginning when he
Oh, all right. I'll tell you what, next time I'll mute it. I wasn't sure about that, but okay. But anyway, so that was fun. Yeah, we're allowed to have fun once in a while, aren't we? So yeah, that's his whole act. He does all of his if you ever catch up with this guy on YouTube, all of his presentations have something to do with technical issues because he is an engineer actually. And so he has like let's just say a different way of doing comedy. But anyway, so if you've never used PowerPoint, well, it's easy to get carried away with all the features. Anyway, all right, so now I've got one more video. This time, this is actually meant to be a quick overview of what statistics is all about. I um, I don't remember how technical it is. I hope it's not too bad because we haven't started yet. But ooh, I think I'll take a chance and show it to you now. Um, if it's too much, well, we'll just watch it again later on. But it's supposed to be an overview of what we're about to do in chapter 12. So let's just take a chance and look at it. I don't think it's too long. All right, let's try this one. All right. Well, that was actually a pretty reasonably non-technical, which is what I was concerned about, introduction to the field. And of course, we already knew about the teacup lady, didn't we? That's right. That was kind of interesting how it came up again in this video. But they did raise an interesting point. What if she had correctly guessed right, or had correctly identified only 7 out of the 8 cups instead of 8 out of 8? Would that have been enough evidence that she knows the difference? Or how about 6 out of 8? Or how about 5 out of 8? So these are the kinds of questions that we could answer with statistics. In other words, you could establish a threshold where you could separate out, getting the tea right by pure chance versus actually knowing the difference. So it's a very broad field, and it shows up just about everywhere you could imagine, and not just in business, but also in a lot of disciplines, like, for example, even biology. There's a major branch of biology called biostatistics, where all the analysis is done on, let's say, the effectiveness of new drugs and that type of thing. It shows up in marketing, as you can probably imagine. Companies have to decide what products to introduce to the public. And how do they do that? Well, they do testing on volunteers, and they ask them what they like and don't like, and they use that information to determine what products make the most sense to bring to market. So it's one of those disciplines that you see it everywhere. And eventually, when the day comes when you have money to invest, it'll also help you presumably make better decisions about what to do with your money. So it's a very broad discipline, and it shows up in a lot of areas. We're just going to be able to barely introduce it to you, but you'll get to learn some important concepts that will be helpful in other areas, not just your major, not just in business, not just investing your money, but just in everyday life. So it's really that important. So first, because we've got a few minutes left, let me just open up chapter 12 so you can see where we're going with this. All right, here we go. Statistics. So we just start out in the beginning. We're going to introduce some new basic definitions. And so why don't we start just with one important one that I want you to be aware of before we even get started. What's interesting about statistics is that you're typically trying to study what's called a population, which is a collection of measurements or outcomes of interest. So the word population normally is taken to mean a collection of people, but here we're looking at it in a different way. We're looking at some characteristic typically of the people that we're studying. So for example, we might be interested in studying not the people themselves, but their salaries or their ages, or where they live, or how many houses they own, or anything along those lines. We can analyze them with statistics, where we'll define the population as not necessarily people, but measurements about those people that we are trying to study for some reason. Like, for example, the government collects a lot of statistics, and they need to understand a lot of details about the population. For example, the Social Security system. It's always in danger of running out of money. They have to know how old the population is to make plans for how to finance the Social Security system. So now, but the challenge though is that the population that we're studying is often extremely large, and it would be unbelievably time consuming to gather up information about every member of a population. So instead, what we often see are samples being used. A sample, as you can see here, is formally defined as a subset of a population. So for example, let me throw one in here right now. Suppose that the government is indeed trying to analyze, not that they don't have all this information, but let's just say they need to do an analysis, wants to determine if the average age of Americans is higher than it was, let's say 20 years ago. If so, changes will be made to the Social Security system. Okay, because obviously they have to find a way to pay for it, but they need to know how much they're likely to need to spend before they make that determination. Whoops, I knew I missed something here. So what they could do, I mean, the two options they have are, number one, the government could actually could gather up and analyze the ages of everyone, of every American. This is the population of interest. Since the population is so large, though, this could be a very time-consuming process. So what can they do instead? Let's just say they decided, you know what, that's too much. That would take forever. We need to know this information right now. Well, another option they have is this. The government could instead take a sample of Americans and analyze their ages. A sample would be a randomly chosen set of Americans. The set would be much smaller than the overall population. Okay, so let's say, for example, they choose, I don't know, instead of the whole 300 million, suppose that the government randomly chooses 100,000 people scattered across the country for the sample. As long as the sample is chosen in such a way that it accurately reflects the underlying population, the average age of the people in the sample should be very close to the average age of the entire population. And so what they've done is they've come up with an estimate of the population mean age or average age, and yet they've saved an awful lot of time. Okay, so, but the key here is this. As long as the sample is chosen in such a way that it accurately reflects, right here, this is the key to the whole thing right here, accurately reflects the entire population, then the results should be very good. I mean, there's no reason why the number that we find in our sample should be way off from the actual population. The key to the whole thing is choosing it correctly. In other words, in this case, just completely at random. We don't just, if we accidentally, let's say, picked only people who are retired for our sample, then clearly the results would be way off. So if we're careful about the way we choose the sample, the results that we get should be a very good, accurate reflection of the population, which is what we're really interested in studying. So this is an important distinction between a population and a sample. So the vast majority of the cases, we're analyzing a population, we're interested in the population, but we actually use a sample to come up with conclusions about the population, mainly because of time and cost considerations. If the population is small, then you may go ahead and study the whole thing anyway. But most of the time, that's actually not the case. So samples are chosen. Or here's another good example, I think. Suppose that Coca-Cola wants to test a new flavor. How about this? What could it be? Pumpkin Coke. Okay, let's say they've decided the public would really like pumpkin Coke, how can they determine if this new product is likely to be successful? One option is to contact every person in the United States and ask their opinion. Since this is likely to be not likely to be feasible, or let's just say this is likely to take a long time, another option is to test the flavor, randomly choose people to test or taste the new flavor. All right, so in other words, you might see them standing around in a supermarket and offering free samples. They could offer free samples to the shoppers in a supermarket. Now, here it gets a little tricky, but if the people who are offered the free samples are an accurate reflection of the entire population, then the results should be very close to the true proportion of Americans who like pumpkin Coke. So in other words, they can't possibly ask every single person in the country whether they like it or not. So they'll pick samples. They'll stand around and people walk up and they say, hey, I'll take that sample. And then of course they expect you to tell them if you like it or not. And you see this all the time with marketing. It's not that uncommon, or at least I guess it used to be more common than it is now, but free samples are a very popular way of getting people's opinions about different products. And so it's a lot cheaper than trying to contact every single person and asking them what they think. So that would be a classic case where sampling is being used to gather information about the underlying population. So anyway, so I just wanted you to get a brief look at the difference between populations and samples, because this is important information for the rest of the chapter. So in the meantime, I see that it's just about 10 o'clock, so we could probably stop right here because I don't want to get too far into this. I think we should save the rest of this for next Monday. And in the meantime, don't forget to hand in the second midterm by Monday night at midnight. So you can take care of that over the weekend if you haven't started. And in the meantime, when we come back on Monday, we'll dive right back into this chapter 12, which is our introduction to statistics. All right. So I hope you had a good time today with those fun videos and of course learned a lot. And I'll see you all on Monday.
Thank you.
Okay. See you next time.
Thank you.
Okay. Bye.